Good afternoon, students. Today we will be discussing about the ultraviolet spectroscopy, UV visible spectroscopy. So that is for the B Pharm 7th semester, and this UV visible spectroscopy may be following different another category also. So what is UV visible spectroscopy? This is a method of determining some concentration and the bond length or the conjugation in the molecular structure. So, we know the light having a range of 200 to 800 and more than above nanometer. So, whereas the visible light having a range from 200 to 400 to 800 nanometer, and below this range there is UV range, that is the ultraviolet range, and the UV light and the visible ray is 400 to 800 and the above 800 that is IR, that is the infrared. So coming to the UV visible spectroscopy, UV light can be absorbed by molecules to excite higher energy and most loosely bound, and electrons from lower energy states to higher state. That means the molecule will be absorbing UV light. As a result, they will be promoted to the higher energy state, from lower energy to higher energy state. The loosely bound means that is the pi electron or the unpaired electron, which will be absorbing the light and they will be excited to the higher energy state. Such transition can be studied extensively to understand the binding energy of the corresponding electron undergoing transition. So from the spectroscopy, we can understand the binding and the presence of double bond or triple bond in a. Since pi electrons are most loosely bound in an organic molecule, UV spectroscopy yields a lot of information about the degree of unsaturation of a molecule. So this procedure may be followed for the determination of the saturation or unsaturation of a molecule. So when the wavelength of the transition exceeds the UV range, based on the same principle, even the color of molecules can be explained on the basis of absorption of visibility. Sometimes the colored molecule also absorb the light, and as a result their concentration can be. Suppose beta carotene, this is a compound of the plant derived sugar, so where the carotene can be having different double bonds. So they are lambda max, this is the absorbing length 452. So they are absorbing different lights, and so through this UV visible, that is the UV light also passed through the some of the solution, and visible light also. So the machine working on the two UV visible spectroscopy. So that light may be visible and they may absorb some by the some. So 452 is a visible length. Now coming to the 1,3-butadiene, that is having the 217 nanometer. This is coming under the UV light. So as a result, UV light will pass through this compound and their bond and saturation will be low. So electromagnetic spectrum. So this is the electromagnetic spectrum you just see here. You can take a screenshot of this spectrum also. So here you can see the visible length having a nanometer of 10 to the power minus 6, 10 to the power 6. So below this visible light, that is the UV light, okay, and above the red, near infrared and infrared. So that is coming under 10 to the power minus 6 or 10 to the power minus 5. So according to the meter, the length is given here as the 10 to the power minus 9 meter, 10 to the power minus 8 meter, like this. So below the UV light, there are some vacuum ultraviolet that is also having very short wavelength, like 10 to the power minus 7 to 10 to the power minus 8. And for the X-rays, that is coming under minus 10 to the power minus 8 to 10 to the power minus 9 nanometer. So if it is converted into nanometer or per centimeter, then we have to multiply the 200 nanometer, and that is a 400 meter. Okay, 10 to the power minus 6 meter, this is centimeter. Okay. And lambda max frequency will be 5 into 10 to the power 4 and lambda max 5.5 into 4. So 1 nanometer equals to 10 to the power minus 9 or 10 to the power minus 6. That is, you have to multiply with them. So as a result, you will be getting results in nanometer. Energy is proportional to frequency. Frequency is also inversely proportional to wavelength. The principle behind this machine is energy is proportional to frequency. So the light having much frequency, then the energy is also high. That means the light which having smaller frequency, they can run faster. So it has been clearly understood that energy is proportional to the frequency. If the compound having higher energy, the frequency will be higher. So you can see the UV rays which can penetrate through our skin very faster because the wavelength is very long, short. As a result, the frequency is also high. And sometimes frequency is inversely and regarding this way, as I said, frequency is inversely proportional to wavelength. That means the compound which having the longer wavelength, they will be lower frequency, and the wavelength which is having smaller and the frequency will be higher. So for this reason, the red light which is having higher wavelength, that is used for the signal so that it can be visible for longer length, and the frequency is short. The visible spectrum again I'm showing with the light effect. So see, we know the waves here, that is the violet, indigo, green, red, and above the red, that is infrared, that is known as the IR, and below the visible range is a visible range. So whenever any monochromatic light or any light ray is passed through a prism, so that is the separating molecule where due to the different refraction, the light will be broken down. As a result, they will be showing this spectrum from violet to red. Okay, so this person angle will be there like this, and if you follow this Webster circle, so here you can find the different nanometer of the violet to red light. These are the visible, right? As we saw, we can see from 400 nanometer to 800 nanometer is the visible range. So violet, indigo, blue, green, yellow, orange, and red. See, you have seen 400 to 620 nanometer. Okay, so these ranges are coming under the visible spectroscopy. So if any compound having these colored substance, they can be find out their structure and their bonding through this colored nanometer also. See, some of the natural organic pigments are there. Alizarin, that is having red color, carmosic acid, and the indigo, this is a blue indigo, fumicin, tyrant purple. So this compound having double one, triple one, or double one saturation, unsaturation. So they can be found out by the physical touch. Prostatin, beta carotene. These are the all colored compound which can be determined through their visible spectroscopy. Now coming to the instrumentation technique, double beam UV spectroscopy. So double beam means the sample and the reference cell will be placed into cuvette, and the light will be passing through the sample cell as well as reference cell. That's why it's called as a double beam UV spectroscopy. So this is a light source. There are different light sources are available, and this is a diffraction grating. The prism will be there, so that will be diffracted the light, and there is a slit which will be selecting particular wavelength. Whenever we are fixing any wavelength, so where we are filtering this slit which will be fixing which wavelength light should be fixed, and there is a rotating disc which absorbs the light or which reflects the light in face of reflection, and the light will be passed through the sample cell, and again the light will be placed in the mirror, and from the mirror again that would be whenever the light is the mirror is rotating and it is rotated, and again the second whenever it will be secondly reflected in the mirror, then it will be again seen as a straight line, and they will be fall upon the detector. As a result, we can found the absorbance of the light. So that means how much light has been absorbed, that by the solution will be detected. Okay, so from the recorder or the instrument having particular recorder or in the computer screen, you can see the demonstration of the graph of that particular domain. So the two lights are passing through the subcell cell and the reference cell, where reference means the standard. You have to fix a standard solution or the blank solution where you have prepared the sample, and the sample cell. If you want to tally with the reference, then suppose you are going to analyze the paracetamol, then you will be taking the standard paracetamol in the reference cell, and you will be taking the sample paracetamol in the sample cell. Okay. So that will be nullify the standard reference cells solution. So light source, combined source used to cover a range of 200 to 800 nanometer. That means a particular light source will be there, which will be covering a range of 200 to 800 nanometer. Deuterium light is also there for UV range, which is hydrogen light actually. And then tungsten or halogen light will be there, that is for the visible range. And now coming to the diffraction grating, the slit. So this is the diffraction grating is there because there is a like glass type of mirror which having a curvature like this, mountain type. Okay? So diffraction grating splits lights to the component colors like a prism, and slit allow to pass through the slit allow to pass only a narrow range of wavelength to the rotating disc. Now, rotating discs are made of different number of segments. So there are some segments like the black section and transparent section and the motion section. From this section, transparent section, the light is passing through. Okay. Now, rotating discs, if light hits the mirrored section, it bounces back to mirror. The reflected light meets the transparent section of the second disc and passes through the detector. Okay, from this reference cell, the light is passed through. And again in the mirror section, the light will be reversed. Detector and computer. If light hits the transparent section, then it will pass through and bounded by a mirror into a second rotating detector. The light meets the mirror section of the second disc and bounces into the detector. Sample and reference cell. Small rectangular glass or quartz container is there, designed in such a manner that the light has to travel 1 centimeter through the contents. Detector and computer is there. Detector converts light to current, and the greater is the intensity of the light, the higher is the current. And an absorbance time could be written as the A locked in I0 by I, where intensity of the light passing through the reference cell is I. Whenever at the past time when the intensity was not, when the light was not absorbed through the sample cell, then we can get the I0 as the intensity, and the light whenever we are passing through the sample cell, it will be I1. I. That is the through sample. Means whenever a sample cell is passed, the intensity of the light is higher. Whenever the light will be passing through the sample cell, whatever the intensity will be that, after that passing through the sample, the intensity will be lower. So you will be measuring the absorbance A log I0 by I. Okay? That is the absorbance formula. So coming to the Lambert and Beer-Lambert law. So Lambert and Beer has combined this formula, log I0 by I equals to epsilon LC. So a Greek letter epsilon, L means concentration of the solution, C sorry, and length of the solution through which the light is passing. That means the sample cell, that is a 1 centimeter, is the cell. So molar absorptivity, what is molar absorptivity? So absorbance of 1 mole of the solution through 1 cubic decimeter if sample cell have to pass a 1 centimeter pathway. Then that concentration is known as the molar absorptivity. The intensity of an absorbed light in UV is expressed as the molar absorptivity. The maximum absorption of the Emax. That means intensity of a particular compound in the UV range is expressed as the molar absorption. It is the maximum absorption into Emax. That means maximum concentration will be absorbed. Now, relative energies of various orbitals. So, for the different structure, different sigma, pi, non-bonding, and pi star, so anti-bonding, sigma star, different bonding orbitals are there. So that will be discussed in our later class. Thank you, everyone.